Welcome to the Bond and Ground Podcast, the podcast where grounding and bonding aren't just topics, they're the foundation of electrical safety. Hosted by CMP5 member Paul Abernathy, this show breaks down the National Electrical Code with a focus on Article 250, the article dedicated to proper grounding and bonding of electrical systems. Whether you're a seasoned electrician or just decoding the code, you're in the right place. No resistance, just grounded knowledge. Now sit back and enjoy the podcast with your host, Paul Abernathy.
What up, everybody? Welcome to another episode of the Bond and Ground Podcast. My name is Paul Abernathy, and it's glad to have you here. It's been a while since we've done a podcast episode on this series. Been mainly focusing on the Master the NEC podcast. If you don't listen to that, make sure you go listen to it. And of course, Let's Ask Paul podcast. Again, as always, you can ask me grounding and bonding questions by going to Fast Tracks System. That's TRAX, by the way, not TRACK. It's Tracks, TRAX. So fasttrackssystem.com. And there you'll see in the navigation, it says, Let's Ask Paul. And you can always ask me questions there, grounding, bonding, anything code related or whatnot. I'm more than happy to answer those questions for you. And so today's question really is really not a question. It's a topic that seems to be still confusing. And of course, we have a grounding and bonding course, and we have a lot of students that are in that. And of course, I've been on the code making panel 5 for many years now. And it's kind of one of my things. I love Code Panel 5. I love the minds that are on that panel dealing with grounding and bonding and helping kind of write that code panel and work with everybody. And the chair, Scott, is great. And again, it's a really a great panel. But we tackle a lot of issues. Now, through the years, I hear a lot of things from many people that tell me they get confused in certain things. And one of the areas of confusion is when we're dealing with supply side bonding jumpers and equipment grounding conductors. Now, it may, if you're in the field and you do this every day, you might be saying, well, I don't know what the confusion is. I know what a supply side bonding jumper is, and I know what an equipment grounding conductor is. That's great. But I've learned that there's a lot of people that do not. And they intermix the two or causes them confusion. And there's one easy thing you can say that kind of immediately could make a 30-minute podcast be 2 minutes and done. And that is, when you have an equipment grounding conductor, it is on the load side of an overcurrent protected device. Okay. And if it's not, then it's something else. It's either a supply side bonding jumper or something like that. So that statement alone for many people will clear it up. But there are a vast majority of people that do not understand the difference between equipment grounding conductors, or acronym EGC, versus an SSBJ, which again, we're moving away from these acronyms, but it's a supply side bonding jumper. And so there is this element of confusion, especially when you have transformers, for example, and your overcurrent protection for that transformer is the first panel. And so from the transformer secondary side up to it, you have a supply side bonding jumper there as well. Now, you may have a system bonding jumper installed in the panel that it's supplying. And a lot of little nuances that go into this type of thing. And again, if grounding and bonding is confusing to you, I do recommend you get our grounding and bonding course. It's a great investment. It doesn't expire. It's a lot of graphics and illustrations, and it's just a good resource to have in your pocket, but it is available. But again, you've also got this podcast, and you can ask me any question you want. I'll do my best to elaborate on it. So again, welcome back to the show. Today, we're going to clear up one of the most commonly confused topics in Article 250, the difference between what is a supply side bonding jumper and an equipment grounding conductor. And we're doing it strictly through the lens of the 2023 edition of the National Electrical Code. Okay, so that's our primary focus. Why not the 2026? Well, because very few states have adopted, maybe even one has adopted the 2026 yet. So the vast majority are going to be either coming into the 2023 or are firmly entrenched in the 2023. And so at this stage, it's probably the most widely adopted edition of the NEC. So it makes sense to kind of focus our discussion on the 2023 edition of the NEC. Now, if you've ever heard someone say, just size it like a ground wire, or they mix up line side bonding with load side grounding, then this episode will make that confusion totally disappear. Because if you explain it to somebody and you understand it fully, then they can grasp it. But a lot of times people are spreading this information, and it's kind of like that old exercise, right? Where you say something in one person's ear, and then they have to translate that to somebody else, and then they have to translate that. It's like you telling your helper, and then your helper telling somebody else or another helper. It's never exactly what you wanted it to be, right? And so that's why we do these podcasts. We want to make sure that we give something that's going to be relevant so that we're passing accurate information along. Remember, safety plus liability note. Now, I'm going to say this to you. This episode is educational. It's based on NEC concepts. Always verify with the adopted code edition in your jurisdiction. Always ask the manufacturer and follow their instructions if in doubt. And again, follow the AHJ. Okay? So those things, with that in mind, remember that the National Electrical Code is a minimum safety standard. And I'm just giving you my opinion on here as somebody that's been doing this for nearly 40 years, written numerous books and articles and blogs, and served on code-making panels and all kinds of things. I'm giving you it from my perspective, okay? So just keep that in mind as we get into this episode. Okay, the big picture. What problem are we trying to solve? Okay, so let's anchor this entire podcast on reality, in one big reality. When something goes wrong, a phase conductor faults to metal, we need a low impedance, ground fault current path back to the source. Did I say source? Back to the source so the protective device can operate. Whether it's a blow a fuse, whether it's to trip a inverse time breaker and whatnot, it's got to activate. So if we have a phase conductor that faults to a metal part that is bonded properly, then it's providing and you've done all the connections properly, you've done everything all the way back to the main panel, then what's happening is that you are actually going to create that low impedance effective ground fault current path by making all these connections properly. And this could happen way out where you have raceways with boxes and connections and through a box, through a feeder panel, all the way back to the circuit. There's elements to this, but the key focus is to be able to trip that overcurrent protected device and de-energize the circuit, okay, on a ground fault. Now, a low impedance path is built by using bonding and grounding, but not all conductors involved are actually the same, and that's where the confusion can come in. And the NEC treats them differently depending on where they are installed within your electrical system. Okay, so that's where the split typically happens. Okay, that's where people tend to kind of get to one point in the understanding, and then they just kind of go to the left or go to the right. Now, on the load side of the service disconnect, and for example, on the load side of most overcurrent protected device, we're usually talking about equipment grounding conductors, which we refer to as the EGC. And everything we do on the load side is relevant to equipment bonding. Okay. And there's a lot of people that get this confused, and they'll say, well, why do you call it equipment grounding conductor if it also does bonding? Well, because there's a note underneath equipment grounding conductor definition that reminds you that it also does bonding. And it's important that you understand that bonding is tying parts together to act as one. So taking a metal box, connecting it to an equipment grounding conductor is going to facilitate them acting as one. They're bonded together. Okay, so there's a whole process that's involved in that. Now, on the line side of a service disconnect, or if you're also talking about when you're dealing with an SDS, separately derived system arrangement, like we talked about in the intro, whereas you have a transformer, let's say, and it's supplying a panel where you're going to have the main breaker and you're going to have a system bonding jumper installed, that type of thing. In that scenario, if we're talking about the line side of a service disconnect or those SDSs, okay, then we're talking about a supply side bonding jumper, and we're talking about on the line side of service equipment, we're talking about service bonding, which typically gets done through what we call a main bonding jumper. And this is also equivalent to what we would call in a separately derived system as a system bonding jumper. Now, I don't want to get it confusing for you in this episode because, again, we have courses that explain the difference in a main bonding jumper versus a system bonding jumper. Essentially, they do the same thing. It's just the main bonding jumper is going to be in your service equipment, typically, and your system bonding jumper is going to be in a separately derived system like a transformer or a generator. It just depends on your situation or the installation. So we want to make sure that we're not venturing into that area because that's a whole separate topic, okay? Now, NFPA, the National Fire Protection Association, itself points out that Article 250 frequently drives you back to 3 core sizing tables within the National Electrical Code, okay? And they are tables 250.102C1, right? And 250.122, okay? Those are your core tables, okay? Now, of course, you also have 250.102D for equipment bonding conductors and all that kind of stuff. So it kind of revolves around those core areas. But those 2 tables in the discussion of the day's podcast are the 2 vital ones that we're dealing with. Of course, there's other tables they'll talk about for grounding electroconductors, 250.66 and sizing of those, okay, which is a totally different topic here. Okay, that's for your grounding electrode system. It's not what we're discussing today. So now that we kind of have those basic core understandings, and if you're confused, again, this is a perfect time for you to send us a response or a comment. And I'll remind you, be very respectful because I am a blocker. I am not here to earn your to clicks and all that kind of stuff. So if you want to come and post crap, then you'll lose the benefit of having access to all this and learning from me because I have a low tolerance for BS. So I'm not going to get into a banter back and forth with people. What I tell you is founded in pure logic in the fact that I've served on the code for decades now. So at the end of the day, you either can accept it or move on, but it is what it is, okay? Now, definitions of each of those conductors. So let's talk about a supply-side bonding jumper, or we use the acronym, and we're familiar with this in the field, is SSBJ. Now, there's a faction of folks out there that don't like acronyms. They don't like the fact that it has, quote, BJ on the end of it. Again, I say grow up, but again, it is what it is. Usually the more liberal side, again, not getting political, but the individual that caused a problem with this is a bit more leaning that way. So I guess we're in a woke world of let's create a problem that really doesn't need to be there. And of course, that also translates in electricians, apprentices. Get over it. Stop making jokes and training sessions and all. Come on, be professional. So it's a supply-side bonding jumper. Now, a supply-side bonding jumper is a bonding conductor or jumper installed on the supply side of the service equipment, like the line side, or within service equipment enclosures, and also shows up in certain separately derived system layouts. The entire point of this is to ensure electrical conductivity between metal parts that must be bonded, so the fault current has a solid return path back to the source, okay, in many cases. All right. Now, it's one of those things that once you install some supply-side bonding jumpers, I have a piece of service equipment, I have raceways coming in, metal raceways that have service conductors in them. I have to bond those raceways. Then I'm going to bond them on the supply side or the line side, basically putting them at the same potential. Then again, it reduces touch potential at that point. That's why also in the code, if you're not familiar with it, 250.142 allows you to use the neutral to bond to metal parts on the supply side. Okay. Not necessarily going to clear an overcurrent protected device, but it's going to keep everything at the same potential and reduce that shock potential. That's the goal here. It's not a perfect world, but we try to do the best that we can under those aspects. Now, key phrases, supply side. Means before the service disconnecting means, or in the line side area of the service equipment. Now, where you don't have the same overcurrent protected device relationship you have on a feeder or branch circuits, a little different, okay? Because when you got feeders or branch circuits, you're dealing with running things on the load side. We're talking line side applications, okay? Typically overcurrent devices for feeders or breakers for branch circuits, that's on the load side. That gears us more towards equipment grounding conductors, which we're going to talk about in a minute. So remember, supply side equates to line side of a service disconnect. All that bonding would be done on the supply side. That's why it's called supply side bonding jumper. That's a bonding component, okay? Now, equipment grounding conductors, referred to as the EGC. You've probably heard that acronym used. Equipment grounding conductor. Now, equipment grounding conductor is a conductor or a recognized metal wiring methods can be utilized like an equipment grounding conductor, like EMT, like rigid metal conduit, intermediate metal conduit, things like that, which have couplings that are listed, fittings that are listed. They all go together and act as one, and they can be in 250.118. If they're listed there, then they can be utilized as an equipment grounding conductor. Doesn't mean you can't pull a wire type equipment ground in there, but it doesn't mean that it is required. Now, some engineers may require it, but that's purely by the engineer design. The NEC is okay with a rigid metal conduit being used as a raceway, as an equipment ground, as it would a wire being run in the raceway, okay? Now, if it's PVC, different story. You're going to put a wire type equipment grounding conductor in that PVC raceway. Does it have to be bare or can it be insulated? It can be either or, unless you're installing it in a specific area that requires it to be insulated, like in a pool situation, those type of things. Then there's different rules for that. But essentially, 250.118, the very first one says it can be bare, covered, or insulated. Okay. Now, of course, the code is going to supplement or modify and change that based on the condition of use. And it may require things like an insulated equipment ground for compliance. Same thing with a 517 for healthcare facilities. You have 517.13a and b, then it's going to require these to have this path, and it's going to require it to be an insulated green equipment grounding conductor, okay? As a redundancy. So different things to be aware of. It can change. That's why it's so important to understand the National Electrical Code. And if you're an electrician, you take your job serious. Just like any doctor, any lawyer, any person, they're always constantly learning. This is why we sell so many of our Master the NEC programs, because it's not an exam prep. That one is an ongoing learning. It's basically an NEC consultant in your pocket. And it also encloses the Fast Tracks Interact as well, which means you could utilize it to ask us questions even when you're in the field. So again, we have a lot of customers that use that. And we have a lot of companies that buy that for their entire staff. And it's basically on their phone, and they got it at any time. Okay? That's just the benefit of that. That's called Mastering the NEC program that we have. It's a good resource. So just kind of remember that an equipment grounding conductor is a conductor, or again, a metal wiring method that's listed in 250.118 that provides the ground fault current path for equipment enclosures and raceways back to the source on the load side. Okay? Load side of that service disconnect. Typically within feeder and branch circuit applications. Now, the NEC recognizes many acceptable, again, EGCs types, whether they're wire type or they're non-wire type, and separately reinforces that the EGC are sized when it's the wire type are based on table 250.122, based on the overcurrent protective device that is ahead of it. Okay, so if you're going to be sizing equipment grounding conductor and it's a 20 amp overcurrent device on a 12 gauge, then you go to the 250.122 and you're going to see that it's going to require that to have, the 20 amp overcurrent protected device is going to be a 12 gauge copper, let's say. So again, understand that it's basically equipment grounds are based on the size of the overcurrent protected device. Now, there are rules in the code. When you increase the size of the ungrounded, those are the hot conductors, because of voltage drop or because an engineer tells you to, because if it's a long run or whatever reason, then other than for adjustment and corrective purposes, then this doesn't apply. But for any other reason, you increase the size of the ungrounded hot conductors to accommodate, again, things like voltage drop or just design, then you have to increase the size of the equipment grounding conductor as well, proportional to the increase of those ungrounded hot conductors. So it means you might have to bump up the equipment grounding conductor size. This is because as you increase the conductor size, because, let's say, of length, you have to make sure that the bigger the conductor can handle more fault current. You want to make sure that in a bolted fault situation or a fault downstream that the equipment grounding conductor is not undersized to choke it and not effectively clear the overcurrent protective device adequately or under a quick fashion. Okay? So you adjust it to accommodate. But many people get that confused as well and don't understand it. And one big problem that we see in this industry is that when people do parallel applications and they don't realize, they go out and they buy MC cable, for example, and you have an equipment grounding conductor that is sized based on that single cable and the size of those conductors and the overcurrent device that is anticipated that those conductors are going to terminate onto. We have a standard called UL 1569 that we have to follow. And it kind of mirrors the NEC's 250.122. But a lot of times people buy these and they want to run them in parallel to get more current because they need it. So they parallel out these MCs, for example. And this also applies to tray cable as well and other cable assemblies. But what you'll find is the equipment grounding conductor in the stock off-the-shelf product is not adequately sized for a parallel application. Okay? And so what happens is, because you're paralleling it, now the overcurrent device is larger because you're trying to get more current out of them. That's the whole purpose of you paralleling it. And now the equipment grounding conductor is not adequately sized in those cable assemblies. Now, there's some allowances. You can do certain things in a cable tray, whatever. We do have some allowances in 250.122F, which we won't get into in this episode. More reason for you to crack open your code book and look at it. And again, you can ask me any questions you have. I told you how to do it. Go to Let's Ask Paul over on our website, fasttracksystem.com. Reference this episode and ask me a question. I'm more than happy to answer. I'm here to answer your questions, folks. That's why I do this. I love answering folks' questions. Right? Now, just remember that there are other things that you have to be aware of in 250.122. Okay? Motor applications, paralleling applications, and all that kind of stuff. But you can't, the example that I gave of paralleling, you can't just take a standard piece of cable and assume that the equipment grounding conductor is properly sized, because there's a high probability it is not. It's only sized for what was expected for that one cable to terminate on the overcurrent device that's appropriate for the size of ungrounded hot conductors that are in that cable. That's it. And you say to yourself, well, why don't manufacturers just make parallels so that it anticipates this with an oversized equipment ground? No, you have to buy it that way. There's no way we can anticipate all of the potential configurations, so no manufacturer is going to do that. It's a waste of money to put more copper, let's say, in an equipment ground when it's unnecessary. So we're not going to create off-the-shelf parallel set opportunities. You order it that way. Okay, enough said on that. Now, the number one difference where they live in the system, for example, is the EGC. Where is this at? The EGC, equipment grounding conductor, that solely lives on the load side. So most of the time when we say EGC, you're talking about feeders leaving service equipment to other panels or other equipment that would be supplied by a feeder, or branch circuits leaving panels, switchboards, disconnects, etc. In other words, downstream of an overcurrent protected device that is clearly associated with the circuit, that overcurrent device is what we're trying to trip quickly. That's where we're going to size an equipment grounding conductor. Okay. Now, the SSBJ, where does it live in this system? We told you earlier, this is a line side application. So supply side binding jumpers show up in the places like service raceways, enclosures on the line side of the service disconnect, meter enclosures, depending on the configuration you're dealing with in your PACO or power company, service conductors in multiple raceways where you must ensure bonding continuity. And again, I told you earlier, many times you're using the neutrals to bond metal enclosures on the supply side under 250.142 gives you that allowance. So you're using those practices. And then also the SSBJs in certain separately derived system layouts where the source enclosure and the first disconnect are in separate enclosures, and you'll be installing the first disconnect in that first enclosure, not in the transformer or the source. So then you would have a SSBJ running up to that first disconnect. Okay, now this is why the NEC treats SSBJs differently. The line side portion of the system is not just another feeder. And I have so many people that we have to correct all the time when they say, hey, I have a feeder to my building. Do you have a service to your building, or do you have really a feeder? Because once you get the terminology wrong and you start propagating that, that's where it can go south. And you think, well, tomatoes, 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 to potatoes, potatoes. It makes a difference, folks. That's why we harp so much on terminology. Yeah, I don't care about sub panel. I mean, we know what we're talking about. I don't care about those type of things. Romex, when we know it's a non-metallic sheath cable, those things we're not losing our crap over. It's when we're talking about code compliance, we're worried about things that really matter, right? Supply side bonding jumpers, system bonding jumpers, equipment bonding jumpers, equipment grounding conductors. Okay, all those things, it's critically important to make sure that we understand it and convey it. Feeders versus branch circuits versus service conductors. Incredibly important that you know the difference, not just because of the nature of the circuit, but when you come up with other things in the code that have to bond and sizing, it's critically important. Because the load size, you're sizing it to overcurrent. The supply side, you're sizing it based on the conductors that are supplying. So it's incredibly important to know the difference, right? So let's talk a little about differences, what they bond, okay? That's important because, again, we know that an equipment grounding conductor also serves a bonding role, but here's where the vast majority of people get confused. EGC bonds equipment on the load side. So think panel enclosure, think disconnect enclosure, think motor frames, think raceways, think boxes, metal boxes, boxes that are feeding utilization equipment. If it is on the load side of an overcurrent device, that's going to be an equipment grounding conductor, or it could be from a box over to a device like a switch or a receptacle. That could be an equipment bonding conductor. But it is on the load side, okay? Load side of an overcurrent protected device. So there is no way in Hades that it is a supply side bonding jumper, okay? Now, it might be an equipment bonding jumper, but remember, load side application, okay? Now, supply side bonding jumper means service side metal parts. Think service raceways, service enclosures. Think of meter can pathways, depending again on the configuration that you're working with, and other metal parts that must be made electrically continuous ahead of the service disconnect. All of that is bonding, and you're bonding all that by using a supply side bonding jumper. This is also why service side bonding details tend to pull in rules about bonding at the fittings, the lock nuts, when you can't use standard lock nuts, bonding bushings, and where they're needed in 250.92. And the service side metal has to be reliably bonded, not probably bonded. You get what I'm saying? In other words, we used to call it some assured bonding, a little bit extra, a little bit over and above the normal bonding that you would have on the load side, okay? Key differences here that you need to lock in your brain to fully wrap your head around it, and it's really going to help you because the biggest confusion people have is not that they know they have to bond. They just don't know how to size things. And so once you distinguish whether or not you're doing supply side bonding versus load side bonding, once you distinguish that and you understand what you're talking about, the rest is just looking up tables and understanding those nuances. And that we can teach you quickly, okay? But you have to grasp these concepts. Now, the difference number 3 is how are they sized? And we've talked about this, we've kind of covered it, but this is the part that either wins or loses jobs. This is where you've identified whether it is a supply side or it is a load side application, okay? And this is where people can get burned. not only if something fails, but also on inspections and also in an investigation where somebody gets hurt down the road, somebody comes in and establishes the fact that it wasn't done properly. An electrical expert like myself, who were looking to get out of this thing pretty quickly, can look around and go, oh, there's the cause. That's why the breaker didn't trip. And this is why it caused. Trust me, it's like anything. If you give us a little bit as an expert on a case like that, we're going to try to find everything we can to tie it back to what was the cause. And so if you do it based on the minimum safety standard, you're covered by the NEC. I hear so many people on social media say, well, my jurisdiction doesn't care if I do this, or I don't have to do this. That's fine. I tell people all the time, you do you, boo. But I'm an electrician. I want to make sure I am CYA at all times. I'm not just wanting to make an inspector happy. And I was an inspector. I was a head of a jurisdiction. Don't make me happy by just trying to meet up something that some jurisdiction just makes up willy-nilly. No. Everything needs to be founded in code logic. Now, I'll get people say, okay, code boy, okay, fanboy. Look, at the end of the day, you're a professional. This is your job. This is what you do every day. You should be looking at that code book on a regular basis, just like your surgeon should be looking at new modern techniques and practices that save lives. You need to take it the same way, constantly filling that beaker of knowledge. Day and day and day. Doesn't matter who you use. Mike Holt has some great stuff. I love Mike. Mike is a great guy. Brian and all them down there, Mike Holt Enterprises, wonderful people. Great programs. We have great programs. Hey, look, I don't really care where you get your knowledge. Just get your knowledge, okay? We want to make better. We're all in this. All of us educators. Ryan Jackson's an amazing educator. We're all in this because we want you to be better educated and do things right. We certainly don't want you to do it wrong. Now, when it comes to the EGC sizing, based on the 2023 edition of the NEC, EGCs are generally sized based on the rating or the setting of the overcurrent protected device ahead of the circuit. That is table 250.122. Now, that's the design philosophy. The EGC, equipment grounding conductor, must be able to carry that fault current long enough for that overcurrent protected device to operate, right? So the mental model for this is overcurrent protected device sizes drives the EGC size with the NEC rules for adjustments per phase conductors. If they're upsized, for example, for voltage drop or whatnot, which could change the size of the EGC. We talked about that earlier. So it might be a baseline to size it based on the overcurrent protected device. But if you increase the size of the conductors, let's say for voltage drop, now you're going to have to see, is this equipment grounding conductor now adequately sized? Because these conductors got bigger. Okay. Now, yeah, the overcurrent device might not have changed, but there is a rule in 250.122b that says, look, if you're increasing those hot conductors because of, let's say, voltage drop, then you're going to have to increase the size of that equipment grounding conductor proportionally. Ignore what you see in table 250.122. That's a baseline. Now you're going to have to increase it. Well, you got to know that. So that's critically important. And so your homework for that is to go read 250.122 and look at A, B, C, D. If you have any questions on those, look at all the way down to F for parallel applications, multi-conductors. Let me know. Holler out at me. Send me a comment. Make sure you reference this episode. I believe this is episode 51 of Master the NEC. Oh, no, actually, this is the Grounding and Bonding podcast. I don't even know what episode this is. So anyway, make sure whatever it is, you look at the title and you reference it, paraphrase what you're asking, and send it to me through the Let's Ask Paul over on our website. I'd love to answer that for you. I'm here. I'm here for you. Now, when it comes to supply-side bonding jumpers, based on the 2023 edition of the NEC, we're going to be looking at 250.102c1. The logic behind that is that your supply-side bonding jumpers are commonly sized using the table 250.102c1, which is specifically used for, also, in case you didn't know this, for sizing grounding conductors, main bonding jumpers, system bonding jumpers, and supply-side bonding jumpers in an AC system. So the mental model that you'd be following is, the largest ungrounded supply conductor drives the supply side bonding jumper size, okay? So again, remember there's parallel applications in 250.122F that you have to follow, but at the end of the day, that's your mental thought process. Now, the reason that this 250.102C1 also drives a grounded conductor, main bonding jumper, system bonding, because all of those are basically sized based on either a load calculation for the grounded conductor. You gotta meet the basic requirements of 250.24, but you also have to understand you have a calculated load you have to meet, and that's going to result in a certain size of conductor, right, to handle that grounded conductor or that neutral current. And also, most of these are all sized based on the size of the ungrounded conductors. See a pattern here? Whereas the equipment ground is not. It's based on the overcurrent device. Key takeaway. Now, why does this sizing logic differ between the two, okay, if it isn't obvious by now? Because on the line side, you don't have the same simple process. The overcurrent protects that conductor. The relationship exists on the load side because on the load side, you have an overcurrent device. It's clearly in series with the circuit and intended to clear the faults on that circuit and shut it down should it be a ground fault condition. Of course, y'all all know that the overcurrent protected device is short circuit, ground fault, and overload. That's why we call it overcurrent, because all three of those conditions are considered overcurrent. So it does all that. But what we're looking at this element here with the equipment ground is we're looking for a ground fault condition. And it shuts off that overcurrent protected device. Now, on the line side, the service conductors and service side path can involve different levels of available fault current, and that has different clearing characteristics. So the code uses a different sizing framework because they are supply conductors and because of the available fault current that may be available and those clearing characteristics. All of that's going to mean that, you know what, the conductor size is going to vary because we don't have the reliability of that overcurrent protector device in play, okay? So the practical takeaway is that if you size the SSBJ by table 250.122, you're often committing a category error, a wrong sizing basis, and your system will not be adequately done. If you're sizing the EGC based on table 250.102C1, you're also mixing systems, and this is confusing everybody, including the inspector. So if you don't get these two things separated and fully understood, remember, EGC, load side, equipment grounded conductors, equipment bonding jumpers, load side. Supply side bonding jumpers, supply side of the service disconnect, or the supply side of the first disconnect on a separately derived system where the system bonding jumper is not at the source, let's say in the transformer. I'm using that as an example, okay? These are key takeaways that you have to be aware of. Now, let's talk a little bit about common field confusion. They go, but it's a feeder, not service conductors. Look, this argument pops up consistently. If in my 40 years of doing this and teaching codes and serving on code panels, someone wants to call something a feeder so they can force table 250.122's logic. So here's a clean way that we like to explain it. You don't decide EGC versus SSBJ by what you want to call it. You decide it by where it's installed relative to the service disconnecting means, or a system bonding jumper if you're dealing with an SDS, okay, relative to that first disconnect arrangement. So look, it's all about where it is, okay? So if it's on the supply side of the service disconnect, then you know it's not an EGC. It can't be. It never can be, okay? If it's part of the service bonding, then you know you're now in the SSBJ land. If you're on the supply side of the disconnect, the conductors are coming into the service equipment. Or from the source, like a separately derived system, to the first disconnect, maybe a panel that's mounted next to a transformer, and the system bonding jumper is located in the first disconnect, then you know that you have a SSBJ situation. It's not an equipment grounding conductor situation. And some people say to me, Paul, yeah, but a transformer has a breaker on the primary side, but that's a separately derived system. It is no direct connection on the primary to secondary. Now, there's a connection between the grounding and bonding components, but that's not what the code says, a separately derived system. It's a separation between primary to secondary. That develops what we call a separately derived system. So the secondary is a new derived system. So for lack of a better understanding, you treat it kind of like a service in the notion of what we're talking about here. Okay, whether you would be a supply side bonding jumper versus an equipment grounding conductor. Why? Because there's no overcurrent device in that source. You get it? I sure hope that nobody out there twists those words because I think it's very clear. And if it didn't, you need to go back and re-listen to this again because I don't know that I can make this any clearer than this, really. So this is why even educational resources and industry training consistently separate Table 251.22 EGCs, load side. Table 251.02C1, bonding jumpers, including supply side bonding jumpers, okay, to the service and on separately derived system applications. That is a supply side bonding jumper, okay? Critically important. Now, a quick chalkboard example you can kind of talk about a little bit, and it kind of helps you kind of hammer this stuff home. Let's see. Let's see, we have a standard service with a raceway on the line side. So you've got the utility, then it's got service conductors, and it goes through the meter, and then it goes to the service disconnect. You have metal raceways and enclosures exist on the line side, whether it's the meter enclosure itself, maybe it's a trough or something like that, a wireway or whatever on the line side that has service conductors in it, okay? Now, you must ensure that the electrical continuity and the bonding of those metal parts are maintained. The conductor you install, identified for that purpose, is called a supply side bonding jumper. Understanding, like I told you earlier, and this is a little more advanced, that the NEC does allow you to use the grounded conductor on the service on the supply side to bond those metal parts, okay? So again, if you didn't know that, that's an powerful thing that can probably save you some money running these supply side bonding jumpers. And you make sure that you're not going to create objectionable current because you don't understand it and you do it multiple times. That can create a problem depending on how you do it. And of course, we can fix it for you. It's some simple fixes. But you just want to make sure that you understand you're either going to use the neutral to do that or you're not. Okay? All right. So anyway, so in this case, you're dealing with a supply side bonding jumper. So you're going to go to 251.02C1 and you're going to base this on the largest ungrounded service conductor, okay? And then you're going to go to 250.102C1 and follow the table and size it accordingly, okay? Now, what about a feeder? So if I have a feeder for service equipment to a downstream panel, we refer to that as a sub panel. Many people like that term. We'll just keep consistent. We'll call it a remote distribution panel. We'll call it a sub panel. I can hear the haters now. So you have your service disconnect, then it's going to a breaker that is feeding conductors that are going to a remote panel, let's say in the basement. Now, you're on the load side. That feeder is protected by an overcurrent protected device, okay? It's in the panel. The grounding conductor installed with the feeder, that is called an equipment grounding conductor. We're not talking about the grounded conductor, which in most cases in a 12240, that's also going to be the neutral. But we're not talking about that. We're talking about the grounding conductor, which is the equipment grounding conductor. It gets run with the feeder. Now, what size does that grounding electroconductor have to be sized? Well, you look at whatever the overcurrent device is that's protecting that feeder. If it's a 60 amp, if it's a 100 amp, whatever, you take it, then you go to table 250.122, go find the 100, move over, and that'll tell you the size, minimum size that you need for your equipment grounding conductor. Makes sense, right? Pretty straightforward. So, what has changed for the 2026? Because people ask that, that type of thing. It's basically, we do have some changes that they have clarified when it comes to equipment grounding conductors, and they never have to be larger than the largest ungrounded conductor in a raceway. This comes into play when you're doing parallel applications. Where in the past, it was very much the way the code was written that you could have an equipment grounded conductor that was larger than the ungrounded conductors that are actually in the same raceway in a parallel application. Now, that is, and there was consensus on this many years ago, and for some reason, all of a sudden in one code cycle, 2026, they all had a brain fart that was on a special committee, and now they're saying, nope, it never has to be larger. Because they forgot that when we run parallel conductors, we time together at the end and they act as one. That is now the circuit conductor. It just happens to have multiple conductors making up the circuit. So that is the circuit conductor. And in the past, it says that the EGC never had to be larger than the largest circuit conductor. Well, if you take all of those blacks and take them together, that is now equivalent, all the circular mills, that is your circuit conductor for at least for that phase or that leg, depending on whether you're dealing single phase or three phase. But they seem to have forgotten that during the meeting, and it was a little group that got together, and at the end, they presented it. And again, I disagree with it because, again, what are we trying to do? We have many, many, many decades of reliable operation from the properly sized equipment grounded conductor, and they changed it. Yes, I'm on that committee, and I tried to argue it. I just hope that people don't get hurt. And they say it's physics, Paul. And I'm like, well, and I asked him, I said, are you telling me that Augustus Soares has been wrong all these decades? And they went, yes. The difference is Augustus Soares submitted data to support it. The Gemini project submitted data to support their position. This code panel submitted nothing. They changed it based on a task group's desire. That's what I'm against. But it is what it is. So either way, I'm going to teach the code the way it's written. I just voice my opinion, but it is, at the end of the day, it's founded in code, and I'm on the record. So, you know what? It is what it is. Okay? All right, folks. And other than that, just some subtle changes in it, but nothing really overly impactful that we really need to go in this episode, because I don't want to turn this into a code change thing. It's not really. Just, look at 250.122 and you'll see that it's pretty consistent, except for that change in 250.122F2, I believe. Other than that, it's pretty consistent to where we've been. Changed a little bit of the verbiage and broke it out into some subdivisions and certain things. But again, same intent. Obviously, I'll do a code change, probably something in the future on that and be more detailed. But again, it's nothing that's going to rock your boat. I pretty much gave you the big crux to the big change for 2026, and that's it. Really all that's necessary. Okay? No. So the takeaways today, EGC is a load side application based on the size of an overcurrent device. The supply side bonding jumper is based on the size of the conductors that are supplying the system. Okay? So it's based on the largest ungrounded supply conductors. Right? All right? That's the primary differences, and it has to do with the location of where we're talking about, whether it's on the load side of the system or the line side of the system. That's what's going to dictate the difference. All right, folks, hopefully you got something out of today's episode and enjoyed it. Make sure you share it with other people. Again, this podcast is brought to you by Electrical Code Academy. If you want to really learn the National Electrical Code, you want to learn grounding and bonding, get our course. It doesn't expire. You can use it in your pocket. And we'd love to have you in our program. And don't forget, we have also message boards that you can chime in and post things and get into great conversations with other like-minded individuals, all available over on our website, fasttracksystem.com. Even if you're a hater, we welcome you to come over there and learn something. Until next time, folks, stay safe. God bless.
Thanks for listening to the Bond and Ground Podcast, the podcast where grounding and bonding aren't just topics. They're the foundation of electrical safety. Hosted by CMP5 member Paul Abernathy, this show breaks down the National Electrical Code with a focus on Article 250 like no one else can. Whether you're a seasoned electrician or just decoding the code, you're in the right place. No resistance, just grounded knowledge. Thanks for listening to the Bond and Ground Podcast. Stay bonded, stay grounded, and as always, trust the real code professionals, not social influencers.